Okay, we are all set. I'm going to pin this and you're going to let me know how the focus is. How does the focus look,
Looks
Sean?
good.
All right, glad to hear it. Welcome to office hours.
Or,
What can I do for you?
Uh, Give me a difficult problem that might be an exam.
Okay. Explain to me what's difficult for you, and I can tailor the problem to you.
Hmm. Specifically around conversions and inversions, that in general.
Can you repeat that, please?
Conversions, contrapositives, inversions.
Oh, converse, inverse,
Yeah,
contrapositive.
yeah.
Okay. The sister conditionals. Shall we review the rules first?
Yes, that'll be nice.
Great. So the original would be something like if P, then Q. Okay? We'll just start with that. Then we have the converse. The way you can remember the converse is converse shoes are on your feet. So the head goes to the feet and the feet go to the head. So we just switch the Q and the P. Then there's the longest word is contrapositive. Contra means opposing, but positive means something positive happens. The contrapositive of the original looks different, but it's the same statement in terms of logical equivalence. These two are logically equivalent. Okay? Do you remember how to build the contrapositive? Okay, so let me see if I can help you. Uh, the contrapositive is the longest word. It's the most complicated word that we have about the sister conditionals. It is the statement that we have to do the most to create.
If not P, then not Q, right?
If not Q,
Ah, not Q.
then
Yeah,
not
that's what I
P.
meant. There you go.
Yeah, we switch the P and the Q and we negate them both. There's not anything more you could do to change the original than to switch the positions of the components and negate both components. Do you see how this is really the most complicated thing we could do to the original?
Yeah, that makes sense.
Good. Now, if you understand that, then you should be able to find the inverse if you remember that the inverse is the contrapositive of the converse. Contrapositives are logically equivalent to one another. So take the converse and do everything you can to switch it around. You will have the inverse. What's it going to be?
If if Q then P.
Well, if Q then P is the converse, we're looking for the inverse. We take the converse and find its contrapositive.
Oh, if not Q, then not P.
You still gotta,
If not P, then not Q.
yeah. If not P, then not Q. So these are the original with the three sister conditionals. Again, if you have a hard time remembering the names, think about converse shoes. They're on your feet. So to get to the converse from the original, the head goes to the foot and the foot goes to the head. To get the contrapositive of the original, we switch around everything that we could possibly switch around. The P and the Q change positions. and we negate them both. And to get the inverse of the original, just understand the inverse is the contrapositive of the converse. So we take the Q and the P and we switch their positions from the converse positions and we negate them both. Another thing that might help you remember these four is that we either leave the P and the Q the way they are and we don't negate them, or we negate them both. None of these is going to have one of the P or Q negated. See what I mean? We
Okay.
always either negate both or we don't negate either when we build the converse. Does that help?
That helps a lot.
So let's start with a simple example, and then we can do a more complicated example. All right, so the original can be if Tia is an adult, then Tia can vote. Okay, that's our original. Let's find the converse. Let's find the contrapositive. Let's find the inverse. Ooh, and while we're at it, we should probably go ahead and practice with the negation. It's a little different. It's not one of the three sisters, right? But that's P and not Q. Okay? P happened and Q did not follow. So we can practice and find the negation as well. Okay, what's the converse going to be? You tell me and I'll write.
If Tia can vote, she's an adult. Tia can
Good.
vote, then she's an adult.
Yeah, it's fine to say she. If Tia can vote, then she's an adult. That is just fine. It's okay to use contractions. Oh, then she can vote. I don't need a contraction there. Getting too excited here. No, she's an adult. I do need a contraction. She's an adult. Perfect. I'll catch up with you. Contrapositive.
If Tia isn't, if Tia can't vote,
Good,
then she's not an adult.
good. In fact, it can be helpful on the test if you make a little key, you know? So if Tia cannot vote or can't vote, then she's not an adult. Perfect. Keep going. Let's do the inverse.
If Tia can't vote, then she's not an adult.
Good. If Tia can't vote, then she's not an adult. And then finally, the negation.
Tia is an adult and she can't vote.
Exactly. Nicely done. So this one was fairly straightforward because P and Q were simple statements. They were not compound statements. Do you agree?
I agree.
So let's play the game with an example that has a compound conclusion. If the sun is hot, then Earth is warm and Pluto is cold. Silly, but I'm just trying to make a simple kind of example. All right, let's write the converse.
Okay. The Earth is warm and Pluto is cold, and the sun is hot.
Okay. We
Then
are
the sun
right.
is hot.
Oh, okay. So you said Q and not P, right? This is our Q and this is our P. But the converse is an if-then statement. So we need an if. If the earth is warm, maybe you said Q and P, but we need an if-then. If the earth is warm and Pluto is cold, then the sun is hot. Do you see what I'm trying to say?
Yeah, that makes sense.
You need an if-then. The only one that's not going to have an if-then is the negation. All right, let's write the contrapositive.
Okay. If the Earth is warm, I mean, if the Earth isn't warm and Pluto isn't cold, then the sun isn't hot.
All right, let's see if I understand what you said. If the earth isn't warm, now I didn't hear the connecting.
And Pluto isn't cold, then the sun
Ooh,
isn't hot.
when we negate an and, we have to use De Morgan's law. What happens to the and in the negation
Gets
of,
reversed. Okay. Yep.
all right, if the earth isn't warm
Or Pluto isn't cold,
or Pluto isn't cold, then
the sun isn't hot.
okay. I'm going to skip the inverse.
Okay.
Let's just go right to the negation. I bet you can do the inverse. If you can write the contrapositive, right, you can write the inverse because you just switch these two components, but they have the same structure. So what is the negation?
The sun isn't hot,
Ooh,
then the Earth isn't warm or Pluto isn't cold.
okay, so I heard a then in there. There is no if or then in the negation because the negation is an and statement. Also, we do not negate the hypothesis in the negation. It's the hypothesis and the negation of the conclusion. You want to try again? Here's the negation up here. We want P and not Q.
Oh, okay, okay, I think got it.
Does that make sense?
Yeah. Uh, the sun is hot, then Earth isn't warm or Pluto isn't cold.
Close. There is no if or then in the negation of an if then. It's an and statement in the negation.
Um,
So the sun is hot and we need commas here because we want
oh,
the earth isn't warm or Pluto isn't cold to be grouped together. And we want the separation to be the and. Okay.
yeah.
Because Q is the compound conclusion. So we want the entire conclusion to be negated in the negation. So the and separates between the hypothesis and the negated conclusion. Shall we do one more?
Yes.
Because there's one situation we haven't really addressed. Sometimes the original might have some kind of a not in it. All right, what do I mean? Let's just rewrite our rules here. For the original, it's if P then Q. For the converse, you tell me what's the converse?
Q then P.
If Q, then P. Good. What's the contrapositive? Good, you're
If not
getting it.
Q, then not P.
Nice. You're getting it. If not Q, then not P. What's the inverse?
If not P, then not Q.
Perfect. And then what is the negation?
P and not Q.
All right. So what if we are given something like this? If the number is real, then its square is not negative. So I've tried to, the number is real is our hypothesis. Its square is not negative. So I've got a not here in our conclusion. So we'll have to deal with not, who's there. Let's write the converse.
Its square is not negative.
If,
If its square is not negative, then the number is real.
good. Let's try the contrapositive.
If its square is negative, then the
Good,
number isn't real.
good. And let's go directly to the negation.
If its square is negative and the number is real. No, no,
Check,
that's not right.
check check your symbolic representations of these forms. Check out what P is. Check out what Q is and try again.
If the number is real, then the square is negative. No, if the number is real and
Hmm.
okay.
Gotta mute my phone. Remember, and we're going to approach this in another way here in a few minutes to help you. Do you remember that every if-then statement is actually universally quantified?
Yeah, I remember you talking about that.
When we negate a universally quantified statement, what is the quantifier of the negation?
It gets switched.
To existential, that's right. So when we negate an if-then statement, the negation cannot be another if-then statement because both of those would be universal, and we don't get a universal statement when we negate a universal statement. Does that help?
That makes sense.
Should help you remember that when we negate an if-then statement, we cannot get another if-then. In fact, we get an and statement. So give it another shot. Here's P, and we want and not Q.
There exists a real number and its square is negative.
There is, yeah, exists or there is a real number and its square is negative. So it just takes a little bit of careful consideration to get these correct. All right, Sean, I'll come back to you as we circle through the room, but let's give somebody else a chance. Who was the next person in the room today? Dylan, I think I saw you.
I think Isaac was here when I joined. So
Oh,
you're
good.
more than welcome to go first if you would
All
like,
right,
Lisa.
Isaac, do you have a question?
Thanks. I guess I was just um could sorry, I'm trying to.
Well, you just got your special homework 4 back. Did you need some help with circuits?
Yeah, actually, yeah, I would say, do you think you could show like a type of questions that you would do for circuits as well as Tarski rules?
Uh-huh. Circuits. This was a do later problem that I introduced in an office hour not that long ago. In fact, if you can find that office hour, you can read the descriptions in the YouTube videos. I write, what we covered so that you don't have to watch the whole video to know what the video is about. So in that office hour, we were talking about circuits. That's one reason why I think you should try to find that office hour. And this was a do later. So why don't we attack this do later? Okay? This would be very typical of a question that you might see on the test, where I give you the Boolean expression. Notice it is in disjunctive normal form. The big operators are OR gates, and inside each parentheses is a complete description of an input state. And from this Boolean expression, we should be able to directly find the I/O table and draw the circuit. So why don't we start with that? So this was a do later. We'll call this example 4. So we're given P and not Q and R, or the quantity P and not Q and not R, or the quantity not P and Q and not R. And you might ask yourself, gosh, why does Dr. Good always give us Boolean expressions that only have 3 parentheses? Theoretically, there could be 8 parentheses. But the answer to that is we only have so much time. Let's draw the I/O table. Because it's in disjunctive normal form, it's extremely easy to find the I/O table directly from the expression, because each one of these Boolean expressions inside the parentheses tells us what the input row is. Let's put P, Q, R, and of course our output is usually S. Doesn't have to be, but it is generally. Under P, we'll write 1, 1, 1, 1, 0, 0, 0, 0. We always put our ones first under P, Q, and R. We've always been doing it this way, and the book does it this way. This is the canonical setup. So we set this 8-row truth table up like this, and our job is to figure out how to fill in the output column. Well, the expression that we are given tells us exactly the circumstances under which the circuit should produce hot output. Hot is true. It means electricity is going to be on that output wire, and it would light up a little light bulb that was attached to it if we actually built it that way. Do you know what P and not Q and R means? Just assume it's true. P is true and not Q is true. and R is true. Do you understand or intuit what this is saying about the input wires for P, Q, and R?
The only thing I know is that it's saying that P is hot and Q is cold and R is hot.
That's fine. That's exactly what we need to know because we write what is true. So this is actually a true statement. It says P is hot and not Q is hot or true, and R is also hot or true. All of this is true. Well, if not Q is hot or true, that does mean that Q is false or cold. So of these 8 rows that we have in an 8-row truth table, well, excuse me, IO table on 3 inputs, which row is associated with P and not Q and R?
Row 3.
Yeah, this is P is hot and not Q is hot, so Q is cold and R. So this Boolean expression says, hey, if this gets input into the circuit, we want a hot output. So we put a 1 here.
Okay, so is it a hot output because the hot outweighs the cold, or
It's a hot output because we describe exactly the circumstances under which we will get hot output. This Boolean expression is supposed to be a recipe that tells us what produces hot output. If we see P and not Q and R as input, that should give us a hot output. Or if P and not Q and not R is what's true, then that should give us a hot output. Or if not P and Q and not R is true or hot, then that situation, that's an input state. That input state yields hot output. So the point of these Boolean expressions is to describe the input states that should produce hot output. In other words, this is a full description of the circumstances under which the circuit would produce hot output. So it's either this is going to happen, or this will happen as input, or this third expression represents the input state. If this happens, or this, we get a 1. So there are 3 different ways we can get a 1 as output. So what row does P and not Q and not R represent? It's an input row.
row 4?
Mm-hmm. That's exactly right. P and not Q and not R. So when you have a hot wire for P and a cold wire for Q and cold for R, this circuit will produce a hot output. Where else should we have S equal 1? What other row?
Row 6.
Not P and Q, not R. Yeah, we had that in our homework, didn't we? All the other rows have O for output because
Okay.
this expression does not include P and Q and R, doesn't include P and Q and not R. It doesn't include not P and Q and R or anything for these last 2 rows either. It just tells us exactly when the output should be hot. Does that make sense?
Yes.
Great. That's why we love disjunctive normal form. It's so easy to get the IO table directly from it because we just read off the inputs and know that those inputs are going to give us hot. So let's draw the circuit. I'm going to write the Boolean expression up top here just because it's easier to see it as a Boolean expression for me. So now we're going to construct the circuit. Now, I noticed a few people, as I've been grading this homework for, made a mistake that is, it's not the most common error, but it happens. Folks not understanding that we scan the expression, we make a note of how many input variables there are. How many input variables are there in this Boolean expression?
3.
Yeah. And that means there are going to be 3 input wires, one for each input variable. That's it. If we want to do something with this p-value, like we want to make it a not p over some time, we can't just draw like a not p here. We can't have 2 p wires coming in. P represents some particular value. It could be hot or cold, but the point is we only have 1 input wire for each variable. That's to know at the very get-go. The other thing that's nice to know when the expression is in Boolean form, this disjunctive normal form, and not just Boolean form, excuse me, disjunctive normal form, is that the very last operator, the very last gate, is going to be this OR gate. So there's going to be an OR gate here at the end. And we always write the word OR inside our OR gate in case we can't draw it quite right. And now it's our job to build what's in between. I like to think of these expressions as being subcircuits. There's 3 of them. And we're going to have to build the 3 subcircuits. One of the subcircuits is going to be for P and not Q and R. Another subcircuit is going to be for P and not Q and not R. And of course, the third one will be for this. Let's take a look inside subcircuit 1 for the expression P and not Q and R. Notice there's an AND gate here and here, and it's okay to feed 3 wires into an AND gate. So we're going to bring the P over. We're going to put a P wire in there. We need not Q, and we don't have not Q yet. So I'm going to pull from the Q wire, and I'm going to draw a not gate. I'm just going to, it can bend, you can make it turn a corner without putting a solder dot, but I'm pulling off of this Q wire to make a not Q. Then, what else do we need to go up into the AND gate that we're going to build here? We've got the P wire, got the not Q wire. Don't we need an R wire? Well, I'm going
Yeah.
to pull from this R. I'm going to kind of pull up here so I'm not in my own way. I'm going to bring it up. When it crosses, it's not touching because I didn't draw a dot. We don't want the R wire tag to cross, to touch the P wire. It can cross it, but it can't touch it. So here we have all 3 of the wires that we need to create the AND gate for expression number 1. You see that? Now expression number 2 is P and not Q and not R. Well, we have a P wire here. I'll pull down from the P wire and we'll bend it through here. We've got not Q on this wire because this was Q, right? This is not Q. We can pull from the not Q and bring it down. And we need a not R. We don't have a not R. We're going to need a not R here as well, but we need a not R now. In fact, we're not going to need a plain old R again, so I'm just going to go ahead and create my not R. And I'm going to bring it up here. So this is not Q and P and not R. They can go through that AND gate together. And that's 2. And finally, we do need not P. We don't have a not P yet. We'll have to pull from the P wire and knot it. So let's take from the P wire. Let's come down here and run it through a NOT gate. So we've got not R, not P. What else do we need in this bottom AND gate, folks?
Not Q.
Well, let's see. Does it say
I
not?
mean, Q, regular Q.
Just regular Q. So I'm just going to bring it down. It's kind of going to be in my way if I come through there. It's going to get too tight. I'm going to bring it down here. I got more room and just bend it. And put them through an AND gate. Just bend it a little bit so that my AND gate's not too big. Then all of these feed into this OR gate. And that's here and here. So if you ran the values from the input states through this circuit, if we actually took the time to run those 8 sets of values, 1, 1, 1. So if we put a 1 here and a 1 here and a 1 here, and we ran them through all of this, we should get an O out here. But if we run P is 1, Q is O, R is 1 through this circuit, so 1 is on P, O is on Q, 1 is on R, then we would get a hot wire out of one of these AND gates. Do you know which AND gate we would get a hot wire out of if we had P is 1, Q is O, and R is 1? This is supposed to be a single wire. I think that should be the first one. P is 1 will be hot going in. If Q is O, so O is coming along here, but it goes through this NOT gate and becomes a 1 because the NOT gate flips the O to a 1. So this bottom wire coming into the AND gate 1 would be hot. And then R is 1, so that'd be hot coming up through here. So all 3 of these would be 1s or hot coming into this AND gate. And we would get a 1 here as output from this first AND gate. And having one of these 3 wires hot would be enough for this OR gate to output hot or 1, because OR will be hot or true if any of the input wires is hot. So you can play that game. I don't really feel like going through all that right now unless I really need to. But that's the circuit. The second part of the do later problem.
Miss
Yes.
Dr.
Question.
Good.
Yes,
Yeah, I actually had to leave in a minute, but this is being recorded, correct?
that's correct.
Okay, thank you so much. I'll make sure to look over this later then.
Okay.
All right, thank you.
You're welcome. Dylan, your turn for a question.
Great. Would this be a good time to ask about the notes you left on my homework that you sent back?
Hang on, let me grab your paper.
I went through them and I think I understand where I went wrong.
Are you in section 9 at 2 o'clock or
Yeah.
section 10 at 3:30?
Section 9.
Okay. Let me just grab it. Let me take a look and I can answer your question about whether or not this is a good time after I see what I wrote. Yeah, that's fine. Are you which one are you looking at?
Well, on um
2B?
let's see.
A lot of
Yeah,
people miss
2B,
2B.
I can see how I completely misread the directions. But
Right.
it
You have
was
to run the values through the way we did in class
right. So you want us to put the binary
on the
before,
actual circuit
yeah.
wires. Yeah. You want
Okay.
me to show you what I wanted, or do you understand?
I understand.
Yeah, we only did it for a couple of circuits in class that had two inputs, so there were only four different values, pairs of inputs to put in. When it's a three input situation like 2A is, you have eight sets of binary digits, three digits for each row to run through to show that you understand. Because, you know, that expression was not in disjunctive normal form.
Right.
I wondered how you were able to come up with those outputs, but we can discuss that later.
Sure.
Other questions from the homework?
Yeah, the last one.
Uh-huh, the negation of that statement.
So if I can guess, I think that it's because I use the language is not real or negative, which implies that it's um not real or um
Yeah.
or it is or it is not negative or something. And I needed to do it
Okay.
the opposite way.
So we have, okay, yeah, let's take a look at special homework for that last question. You are not the only person who missed that.
Wait.
So the original question was, I've got this printed out here somewhere close by. Do you want to read the original to me?
Yeah, I can.
That would be
It
helpful.
says if a number is real, then its square is real and non-negative.
If a number is real, then its square is real and non-negative. And I think we went through something like this in class. So we have an if P, then Q. And we want to first realize this is definitely, universal because it's a conditional. So its negation needs to be existential. You got that part fine. It's a quirk of English.
I see it now.
Yeah, let's see if we can write a correct negation. There is a real number, or you could say a number that is real, but I'll say there is a real number whose square is not real or is negative. This is correct. This would be a correct negation. When we
Is being the key word that I missed there, I
Yeah,
guess.
yeah. When we get a little lazy or we think, oh, I don't have to, you know, I can get away with not writing, as much. Um, then we get, incorrect negations. I'll write a couple of them and we can discuss why, they're incorrect. There is a real number having a square that is not real or negative. When we put the not in front of this or statement, this not is actually being applied to both of the components in the or statement, and it becomes an and statement. This really means not real and not negative. It's De Morgan's law in disguise, and that's not what we want. This was a very, very common error. So I'm glad you brought it up, and I hope that folks can understand that sometimes the best way to get it right is just to thoroughly address and the words and not try to cut corners. Cutting corners is always a mistake.
Right.
Did you have other questions?
No, thank you.
You're very welcome. Malayla, it's your turn. Do you have some questions?
Yes, I was wondering if you could go over empty set.
Go over the empty set?
Yes, please.
Sure. The empty set, it's an interesting set. The empty set is unique. There is only one of them. So by definition, the empty set is the set that has no elements. It has no elements. Okay, so there's some things to understand. There's notation. You can use set brackets with nothing inside. That's like the empty bag with no elements rattling around in the bag. Okay, but the bag is there. The empty set is not nothing. It's the set that has no elements. Or if you prefer, you can use this symbol, but you don't want to use both. So one of the things we have to be careful about is, this idea, hey, if this is good and this is good, maybe using them both is even better. But that's not the way it works when it's the empty set. When we put set brackets and then we put the empty set inside, this is not an empty set. It has an element, namely a single element, the empty set. So we don't, this is wrong notation. One of the other things that we learned about the empty set is there's a fact. Given any set X, the empty set is always a subset of X. And that's because to check if a set is a subset of another set, what we do is we ask this question: is every element in the set that we're trying to prove is a subset also an element over here in the superset? X is called the superset. Well, there aren't any elements to check. So that relationship is true by false hypothesis. The actual definition goes like this. Empty set is a subset of X because a little x element of X of the empty set is false. So X being an element of the empty set implies X is an element of X, and that's actually what we're checking. This is what we check. For subset inclusion. What are you doing, Pup? Are you stuck? You stuck back here? This if then is true by false hypothesis because there is no element X in the empty set. So this hypothesis of this if then is false. And what we know about if then statements is if an if then statement has a false hypothesis, the entire if then is true by false hypothesis. So this is true by false hypothesis. And that means the empty set is a subset of any set, including itself. So, here's a sort of odd application of the fact that the empty set is a subset of any set X. We didn't say anything special about this set X. It's just a set. It could be the empty set. The empty set is a subset of the empty set. That is true. The empty set is a subset of every set. Does that help?
We had a question about that. And could you go over that, please?
I don't know what question you're talking about. Can you
It's
tell me?
question 4 on special homework 2.
Sure. Special homework number 2.
Yes.
Question number 4.
Mm-hmm.
Uh-huh. Hang on, let me just grab that. I need to go and look at special homework 2 and grab. So in problem number 4, we were referring to sets A, B, and C from above. So we were going to use sets A and from the problem above, and that was problem 3. And so set A had the elements little a, little b, little c, and little d. B had the elements little a, little e, and little f. And C was a set that contained elements little b, little c, and little d. And the directions in 4A were to complete the statements to make them true. And the first statement said blank is a proper. Oh, do you know the difference between proper subset and subset?
Well, I saw the definition of it in the notes, but I don't really understand it.
Okay, let's talk about the difference between subset of and proper subset of. Subset of just trying to get back to Zoom so I can make sure you can see what I'm writing. Subset of is this sort of definition. In fact, the general definition of subset of, if we're given sets, let's call them X and Y. subset of versus proper subset of. And this is in the book. It's a good chance to use the search engine and just search proper subset of, but we can get the definitions here. Given sets X and Y, definition 1, we say X is a subset of Y if each element in set X is also in set Y. And if we want to write that definition as an implication, it would be something like this. For all elements little a in the whole universe, little a being an element of set X implies little a is an element of set Y. If this is true, this is the same thing as saying X is a subset of Y, okay? Every element little a that's in set X is also an element in set Y. Proper subsets a little bit more, still sets X and Y to play this game. We say X is a proper subset of Y if it's a subset. So that's the first thing. X actually has to be a subset of Y. But then, in some sense, Y has to be bigger. There's got to be something in Y that's not in X. You see, because X can be a subset of X. That's always true. Everything that's in X is an element of X. But X is not a proper subset of X because X cannot have more elements than it has. So here, the second property is Y has at least one element B, where B, little b, is not in X. So another way to think about it is Y is not a subset of X. So I'll give you an example. If X has the elements 1 and 2, and Y has the elements 1, 2, and 3, X is a subset of Y, but Y is not a subset of X because 3 is in Y and it's not in X. So X is a proper subset of Y. Sort of like strict less than. Y actually has more than X. But X is not a proper subset of X because it has exactly what it has, even though X is a subset of X. X is definitely a subset of X, but it can't be a proper subset of itself. It can only be a proper subset of a set that's bigger. Okay? Does that make sense?
Yes. So the proper subset would mean that um Y just has one more element than
Could be,
X.
oh, it could be lots more element. Here's one.
No, not
Let's,
just one, but like
it,
it has elements that X doesn't have.
that's right. Like Z, just the integers, that is a proper subset of the reals. The reals have lots and lots of numbers that aren't in Z, but all it takes is one for proper subset inclusion, as long as we have the subset inclusion. So here we have these three sets, and we're asked to complete the statements to make them true So blank is a proper subset of both B and C. Well, do B and C share any elements in common at all?
No.
They don't. So there's really only one set that could be a subset of both B and C, and it happens to be a proper subset of both B and C because it's the empty set. The empty set's empty. It doesn't even have any elements. It is a subset of B because the empty set is a subset of X for any set X. And since B is not empty, the empty set is a proper subset of B. The empty set is a proper subset of C for the same reason. It's the only possible answer to that. Does that make sense?
Mm-hmm.
And when you look at the structure of the special homework, if I share my screen to show you, it was sort of supposed to kind of help you. Bigger. This whole section on problem 4, well, this whole section, problem 4 was preceded by some stuff about the empty set. Okay? So that was supposed to kind of clue you in that this whole part was about thinking about the empty set.
Okay.
Okay. And you know the answer to 4B now? Blank is a subset of the empty set here in 4B. What could?
A.
Well, A has lots of, well, A has 4 elements. Is A a subset of the empty set? That means every element in A would have to be an element of the empty set because the subset, you can think of the subset symbol as being like a less than or equal to symbol in some sense. So whatever we put here, all the elements in the set here have to be elements in the superset. But are there any elements in the empty set superset?
No.
So there is only one set that could possibly be a subset of the empty set. And that is the empty set itself. Okay,
Mm-hmm.
good. Sean, it's your turn. Do you have a question?
Thank you.
You're welcome.
No questions from me. I was observing. That's all. Thank you.
You're welcome. Malayla, do you have another question? Malayla's gone. Okay, folks are gone. Goodbye.